Hello everyone, today I want to show you how to program or simulate a 1 degree of freedom single mass system from scratch. And we're going to program it in C. And in the first part I'm going to show you how to derive the systems of equation for the system, and in the second part I'm going to program it from scratch. So let's start directly with the first part. First we need a system. So we start with a wall and a floor or ground, and this is going to be our single mass with mass m. Let's put some wheels on it, so the whole system is frictionless. We're going to connect a spring from the wall to our mass, and we assume that this is our single coordinate, which is called x. Our spring gets a spring constant c, and we assume that the spring is the spring's unloaded length. We'll just call it L0. We don't really need it because we design our coordinate system in such a way that we are at 0 when the spring is at its unloaded length. So we don't really need it, but just something to keep in mind, that the spring always has an unloaded length. So there is, in the equilibrium state, when the mass is at 0, there is no spring force acting on our mass. So what do we have to do next? In order to derive the system's equation, we have to have a look at what forces are actually acting on our mass. So let's just draw the mass without the rest of the system. We can assume, or we will assume, for this case, that the mass is moving in the positive x direction. So the speed is not really relevant for this, but let's just assume the mass is moving in positive x direction. So if we deflect the mass to the right, we can see that we are in positive x, so the spring is going to act on the mass with a negative force. So let's draw our negative force, and of course we're using a proportional spring, so the spring force is simply the spring constant times the deflection. The second law of Newton states, or Newton's second law states, that a mass is going to move indefinitely in a direction unless a force is acting on it. So we have the inertia of the mass that we have to consider. And the inertia is, of course, in the opposite direction of the movement, or the velocity vector. So let's write down the inertia of the mass, the force of inertia, and this is the mass of the mass times the acceleration, and the acceleration is the second derivative with respect to time of the position of the mass. So it's mx dot dot. So if we write that equation down, we have the negative m times x dot dot minus cx, and we don't have any other forces acting on the mass, and this means that this is equal to 0. And of course we can write it in a different way. We can multiply with minus 1, and we get this equation. There we go. Now we have an ordinary differential equation for our system that describes the state of the system for a specific initial case at any point in time. And the system is homogeneous since there is a 0 at the right side, or on the right side, and the system is ordinary since we only have one variable, and it's with respect to time. So if we want to solve this equation analytically, there are a number of different ways for solving this equation. One of them is to just guess a function, and that's what I'm very sorry about that. That's what we're going to do now. So we have x, and we assume that our function is going to be a times e to the power of lambda times t. So that's x with respect to t. That means that x dot dot is a lambda squared e to the power of lambda t. So now that we have the two functions, we can just insert them into our original function. So it's m times a times lambda squared e to the power of lambda t plus c times a and e to the power of lambda t. Oh, that's a lambda and not an x. And this is of course still equal to 0. So if we have a quick look at this equation, we can see that we can divide by a. And we can divide by a because a is certainly not negative. Because if we have a quick look at our system, if we were to choose a as 0, then x would be 0, x dot dot would be 0, which will also mean that the velocity of the system is 0. So the position is 0, the velocity is 0, and the acceleration is 0. So that means our mass would just be standing at the equilibrium state. There is the unloaded spring length, so we are not moving, we don't have any forces acting on the mass, and we don't really want to consider this case since it's trivial, of course. So we can assume that a is not equal to 0, which means we can divide by a and remove a from the equation, since 0 divided by a is of course 0. So we have m lambda squared, but we can also see that we can factor out the e to the power of lambda t. So we get this equation. There we go, is equal to 0. So we can also easily see that this expression, e to the power of lambda t, is also not going to be 0. So that only leaves us with this expression, which has to be 0 in order to solve this equation. So let's write that down. We receive m lambda squared plus c is equal to 0. And we can solve this equation quite easily for lambda, of course. We subtract by c, divide by m, so we get minus c divided by m. But we have a square, so we have to take the square root, and it can of course be positive and negative. Ooh, that's not very pretty, so let's write it down again. So these are our two solutions for lambda. We have plus minus square root of minus c divided by m. And now that we have the solution for lambda, we can go back to our original function and insert it into our original function. So the solution, the universal or common solution for x is a times e to the power of, let's go with the plus first, minus c divided by m t plus b, because we have two solutions, minus square root of minus c divided by m times t. There we go. So now that we have this equation that completely describes our system, we can, if we have an initial set or an initial state of our system, we can then describe the position, the velocity, and the acceleration of the system for any point in time for a specific set of initial states, for a specific initial state. So for example, if we know, okay, at time 0 we are at x1 and we have velocity 0, we can then compute A and B, and we will have a complete solution for our system for this specific initial state. So now, how does that tie in with our programming? Of course, we're not going to program the solution, the analytic solution in our C program. We are going to integrate numerically. So let's go back to our initial equation, which was this one. And there are a number of different ways to integrate numerically or to compute something numerically. And we're going to take a look at the most simple way of computing that. So if we assume this is our time and this is our slightly wrong. This is our displacement. There is a formula called, of course, the explicit Euler. And explicit Euler is basically a way to extrapolate and to compute the next step in time numerically. So what does that mean? It means if we have a position, we have the next position in time, n is the time step, since we are computing on a computer and we can only look at discrete time steps. So we can only look at the system here, we can look at it here, we can look at it here, and so on. We can only observe specific discrete moments in time. So we have our current position, our current time step, which is n, and we're going to say, okay, if that is n, and this was our position, we can then have a look at the derivative of x, which is the speed, and we have this space in time that we cannot observe, but we can simply say, okay, this is our derivative, so we're going to compute the position change for this, I'm just going to say it's blind spot, or for this delta t, and this will give us the next position in time. So it's basically our old position plus the velocity multiplied by the time step, which is usually referred to as h. And of course we can also do that for the velocity. So we can say, okay, our velocity in the next time step is our velocity in the initial time step plus the acceleration times the time step. And exactly this is what we're going to, like these two formulas are the ones we're going to use in our C code to compute the position. So let's start by creating a new fresh C file. So we're going to call it 1degreeoffreedom.c. First we need to include the standard in-out, because we of course want to output our data. And that's about everything we need concerning includes. Then we can start right away with our main function. Let's return 0 right away so we don't forget it. So what do we actually need for our simulation? So let's have a look at our system again. Our system is here at the top left. We have a single mass that has a specific weight. We have a spring that has a spring constant. Then we have our equations that we want to actually program into our program. We have the position, the time step, the velocity, and of course the acceleration. So, and in order to have everything a bit more ordered, we're going to put everything inside a struct. So let's call it struct mass. And it's also very useful if you have more than one mass. Then we could go struct mass 1, for example. So let's go. We start with the mass, then we have the spring stiffness, we have our position, we have the speed of the mass or the velocity, we have the acceleration. And that's it. So let's create a mass by calling struct mass mass, and we're going to initialize it to 0. Then, as I've mentioned, we need a time step. We are going to go with 0.01 seconds, which is not too small, but also not too big, because you can have problems with numerical instability if your time step's too large. Then we of course want to simulate a specific time, like in the real world time. So let's say we want to simulate 90 seconds of real world time. And of course, if we want to simulate the time, we need a specific amount of simulation steps, because we have the simulation time divided by our time step, which is the amount of steps that we have to take in order to reach our specific, or to reach our desired time, basically. And we're going to cast to int, because our simulation loop is going to rely on integers. So what else do we need? Currently we have our mass initiated to 0, but if we have 0 mass, that's not really useful, and it's probably going to create some problems later on. So we need a mass, we need a spring stiffness, let's give it a 10. Then what else do we need? Currently we have position set to 0. Let's go back to our system. If we have position 0, we do not have any spring forces acting on our mass, so the mass is going to stay at 0 indefinitely. So that's also not very useful. So let's go with an initial position of 10 meters. We're going to be calculating everything in SI units. So let's go on. I think we have everything covered so far, so we can move on to our simulation loop. So let's add a comment. We have the Explicit Euler simulation loop. There we go. No, didn't want that. That's what I wanted. Okay, so let's start with our simulation loop. What we want to compute or simulate are these two equations. So let's start with the position. We need the new position is the current position plus the velocity times the time step. Okay, we have everything for that. So let's go. We have the new position is the current position plus the speed times our time step. That was pretty easy. Okay, let's move on. Next, we need the speed or velocity is our current velocity plus the acceleration times the time step. Oh, that was a slight mistake. And we have the acceleration times our time step. There we go. So now we only have the acceleration missing. But if we take a look at our initial equation, we can see that the acceleration is right here. So let's write it down. This is our acceleration, x dot dot plus spring stiffness times position. Okay, is equal to 0. So we can easily solve this equation for the acceleration, which is minus spring stiffness times position divided by the mass. So we can just put it in here. We have the spring stiffness and the position divided by the mass. There we go. And of course it's minus. And I also made a small mistake here. there we go. So what are we computing now? We have our position here, and the velocity, and the acceleration in the middle. And that's exactly what we have here. We have the new position is the current position plus the speed times the time step. Then with the new position, we get a new acceleration with the spring stiffness and the mass. And with that acceleration, we're going to get a new speed, which is current speed plus the acceleration times the time step. And then we reach the end of our loop. We go to the next time step. We have a new speed, which is going to give us a new position, a new acceleration, a new speed, and so on. And that's how we're going to loop over that. But we're missing something. We're missing the actual time that we are at in our simulation. So let's introduce the time. And the time is the old time plus the time step, of course. So we are just counting upwards. And now that we have our simulation loop, we would probably want to have a look at our results. And the easiest way to have a look at our results is to write them to a file. So let's create a file pointer and let's open a file. I am using Windows, that's why I'm using fopens. And let's call our file .temp. And we're going to write to it. What the W actually does is it creates a file if there's no file present, and if there's a file already present, then it deletes the file and just starts a new file with the same name. So now that we have a file open, we can write to the file by using fprintf. And we want to write two doubles, and one of them is the time, because we want to have a look at the position over time, and the other one is of course the position. So that's basically everything that we need. Let's have a quick look if it actually compiles. There we go, compiled fine. But now we have the problem of having a look at our data. So now we are having our simulation loop, we are simulating everything, but we can't have a look at our data because we would have to take our file, our data.temp, and then we'd have to put it inside LibreOffice, for example, to visualize the data. But of course that's not really feasible, at least not in this scenario. So let's create another file pointer, and what we are going to do with that file pointer is we're going to create a pipe, and we're going to use popen or underscore popen, of course, because I'm on Windows, and we're going to use that pipe to send a stream of input to GNUplot. I have GNUplot installed on my PC. I'll probably make a video about how to use or set up GNUplot in a different video, but for now that's all you need to know. We also have to send some commands to GNUplot. We are our pipe, because we have to tell GNUplot what to do, of course. So let's set a title. We're going to call the title 1 degree of freedom system. Oh. No, that's wrong. There we go. And we are going to tell it to plot our data.temp file. Like this. And I did make a small mistake. Of course, I need an array. Yep, there we go. So now that we have our pipe, we have our commands. Now we actually have to send the commands to our pipe. And in order to do that, we are going to create another little loop in which we are going to be sending two commands. That's why I'm having a 2 here. And we're going to fprintf. It's going to our GNU pipe, and we're going to send a string, new line, and it's GNU commands, and that's it. These are our two commands that we want to send. And as you can see, this is a very simple program. We have everything hard-coded. So if we wanted to, for example, change the mass in order to do some tests, for example, we would have to, of course, compile the program again. So let's have a look. Let's compile it real quick, and let's hope everything works out as expected. And there we go. Now we have our simulation. It's 90 seconds. As you can see, we don't have any damping in the system. We get a nice, even oscillation of our mass. Our mass is basically moving back and forth. And that's everything we wanted to see. So now that we have verified our program and everything is actually working, we can have a look at a few phenomena. For example, if we take a look at our analytic solution, we can take a look at this expression, which is square root of minus spring stiffness divided by the mass. And this expression actually describes the frequency with which the system oscillates. So, for example, if we reduce the spring stiffness, we would expect the frequency of the system to also be way lower. So let's do that real quick. Let's go to our spring stiffness up here, and we reduce it by about factor 100. So let's compile our system real quick and run it, and there we go. As you can see, the frequency of this system is way lower than it was before. So now that we've had a look at the frequency of the system, we can also introduce damping, because right now our system is not really that interesting. So let's add damping to our system. Let's call it up here. And of course damping should be different, should be non-zero. So let's go, we should probably increase the spring stiffness again and add damping of about 0.1. But of course we need a new equation to describe our system, because right now we only have the spring stiffness. But if we have damping, damping is always in the opposite direction of the moving mass. So that means that damping is in the opposite direction of our x-coordinate, and damping is also dependent on the speed or on the velocity. So we can use, for example, k as our damping coefficient, and that multiplied with x dot is going to be our damping force. And if we take this equation and add the damping force to it, then we can easily see that it's mx dot dot plus k x dot plus cx is equal to 0. And the only thing that really changes is the way we calculate our acceleration. So the acceleration then becomes x dot dot is equal to minus cx divided by the mass minus kx dot divided by the mass. And we can easily modify our program by just adding this part. So let's go to our acceleration and let's add our damping times the speed divided by the mass of the system. And let's quickly compile our system and have a look. There we go. Now we have introduced damping. As you can see, the amplitude of our oscillation is reduced. Yeah, and that's basically everything I want to show you. I hope you enjoyed the video and have a nice day.